Hello everybody, this is the last lecture for our thermodynamics chapter. This lecture is going to do calculations of Gibbs free energy, and we're going to start connecting it back to equilibrium. So we're going to connect in an entirely different chapter. That's one of the great things about thermodynamics, is it really allows us to connect things that may have seemed separate before. We're now going to see that they're all interconnected. That is something that happens a ton in AP problems, is the connection between thermochemistry, thermodynamics, kinetics, and equilibrium. They love to mix and match those things all together to show you all those topics being connected. So let's get to it. It's going to be time for some math. These math problems are going to get a bit more involved, lots of moving pieces, but you know how to do all the baby steps. We just have to get comfortable and proficient and fast at putting them together. So we've learned a little bit about Gibbs free energy, right? It's the amount of work that can be done. We call that the chemical potential. Because we're in chemistry, right, we're not worried too much about mechanical type systems like physics is. We're looking at the chemical potential here. Remember, not the same as enthalpy, right? It's more complicated. It's a more complicated type of energy. So we're going to do some playing with rearrangements for a minute, okay? So just kind of hang in there and you'll see where I'm going eventually. So we saw last time when we were learning about entropy that the change in entropy to the universe is the sum of the system plus the surroundings. And we learned that the delta S of the surroundings is the same as negative delta H over T for the system. Well, now I can take this equation that we saw last time, and I'm going to start playing around with it a bit. I'm going to multiply both sides by t, okay? Let's say I don't like this in the denominator. Let's get rid of that. We're going to multiply everything by t. It's going to turn into this. That doesn't seem super helpful yet, but we're going somewhere, okay? Now, I'm going to rearrange this a little bit, okay? I'm going to move some things around. I want to get this negative delta H gone. I'm going to move it to the other side. I'm going to kind of move some things around. And this is going to turn into this instead. It's the same equation, okay? It's just in a slightly different format. Now, this equation should remind you of something. What does this remind you of? This is very similar to an equation we learned early in the chapter that we introduced you to and we're going to come back to today. This looks a lot like our Gibbs-Helmholtz equation, doesn't it? So let me kind of go back and forth. Delta H minus T delta S, delta H minus T delta S. So that's helping us connect the entropy of the universe to Gibbs free energy. They are connected. You can see here, right, they're functionally the same. Therefore, because the change in entropy of the universe decides whether something's spontaneous, that's why delta G can determine if something is spontaneous. If delta S of the universe is positive, then delta G ends up negative. So that's why a negative change in a negative change in Gibbs free energy can be used to determine if the change in entropy of the universe was positive or not, which is the same as deciding whether something's spontaneous or not. And remember our big important fact, that negative delta G, right? Being spontaneous, big deal. Just a little something funny to throw in there for you. All right. Mental math, okay? This is something that does not come naturally to everybody. And the best suggestion I have, if you're struggling with this mental math that we're going to do, is to practice out loud. You're going to feel really silly sitting in your bedroom talking to yourself, right? But it's important to do. Our brain works differently. We remember things differently. We can recall things differently when you've heard it and said it out loud, okay? So it's very, very common for you to be asked whether something is spontaneous or not just based on the algebraic signs of delta H and delta S. So what we're going to have to do is use our Gibbs equation to see if delta G ends up being positive or negative. So let's give this a go. What I've tried to do is I've tried to organize this in a chart that we can go through stepwise. And then you can come back and look at the glue-in later, and you can kind of talk to yourself and say it all out loud. Okay, hopefully this can be helpful to you. The best combination, the most favorable that we can have, would be if we had an exothermic reaction and an increase in entropy. So negative delta H and a positive delta S. That will always result in a negative delta G. At any temperature, it doesn't matter what temperature you have. So let's kind of think through this. If we have a negative number and we're going to subtract a positive number, and we're using Kelvin, so temperature is always positive, a negative minus a positive will always give you a negative number. That's what you have to be able to think through in your brain. Negative minus a positive is a negative. All right, let's look at the worst combo, something that will never ever be spontaneous. Endothermic and a decrease in entropy. That is not good. That will never ever be spontaneous. It will always be positive delta G at any temperature. So let's talk through it. A positive number minus a negative number. Positive minus a negative is going to be a positive. What's a minus of a negative, right? Positive. So this is functionally plus positive plus a positive. Double negatives can't trip you up. You gotta get used to and good at those double negatives. That leaves us with a few combinations that are what I call variable. These combinations are going to depend on the temperature that the reaction is occurring at. These are the ones that can be a little bit trickier. So, for example, let's say we have an endothermic reaction. That's not favorable. That's not good. But we do have an increase in entropy. There is a possibility for delta G to end up negative. Do you see how I put it in yellow? Like a maybe, right? This is only going to happen if you're at a high temperature. And what we should say is a sufficiently high temperature. What counts as high is going to depend on the specific equation, specific reaction. So I don't have a good answer for you about what counts as sufficiently high. It depends on the specific numbers. But what we can do is think about the concept here. I have a positive number minus a positive. Well, what circumstance would allow that to end up negative? only if your entropy component is sufficiently big, right? You need a small number minus a big number to end up negative. So T has to be big enough that this part right here can overcome the bad enthalpy situation. So your delta H needs to be smaller than T delta S, or T delta S needs to be bigger than your enthalpy. Let's look at our other variable combo. This time, let's say it's exothermic, so we have a good situation for our enthalpy, but entropy is decreasing. There is a possibility for this to still end up spontaneous. But this time, the temperatures need to be sufficiently low. If we have a negative number minus a negative number, we need this to turn out negative still. So you have a negative minus a negative, so that's actually negative and a positive. So you have to make sure that your delta H is going to be a larger negative than T delta S, which sounds really complicated. A larger negative is actually a smaller number, isn't it? So if you look, that delta H less than is still true, isn't it? These double negatives can scramble your brain, okay? Practice, 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 practice. That is the only way to get proficient and quick. When I first learned this, I felt like my eyes just crossed and I just zoned out and I went, I have no idea what's happening. And you can't do that. You gotta buckle down, you gotta push through, you gotta make it work. Now, one thing that we are up against that I don't personally care for is a time crunch on our exams. The AP exam is timed. Our quizzes and tests will be timed the same way because we're in AP chemistry, getting ready for the AP test. We have a time crunch. So the best thing to do here, if your brain is feeling scrambled, is you need to just flat out memorize the combinations. That might be best for you. That might be fastest. It's going to take more time. It's going to make conceptual problems potentially more difficult if you don't understand why it works. But maybe in the beginning, this is a place to start. What I like to do, because I'm lazy, and I'm not the one taking the timed test like you are, is I like to kind of write out the plus and minus signs and walk through the Gibbs equation myself. I like to kind of go, okay, positive minus a negative, that's plus and plus. Okay, that's going to always be positive. I like to kind of walk through. Maybe you find some trick. Maybe you have some mnemonic. Tell me if it's cool. I'll add it. Okay, I'd love to do that. But what you can't do is you can't shut down. I entirely believe that the purpose of this class is to get you ready for college chemistry by teaching you to not shut down. I think that is the deciding factor on how you do. Is you cannot let your brain shut off. You can't shut down. You just gotta persevere, right? You gotta push through. And this is one of the best topics to practice that on. That mental math, that's tough. I've given you a printout. I only have a black and white printer, so I have a black and white copy that you have. You could color code it like this, or there's a color copy on the website if you'd rather print your own that's color coded. I put the best combo, worst combo, and the variable combos in those different colors. I really like this one. It's very simple. It reminds me of those Punnett squares in biology. So maybe that one you like. If you find another, let me know. Okay. All right, on to some more calculations. Method number 1, using the Gibbs equation, right? Find your delta H, find your delta S, plug it all in, find delta G, okay? One thing to understand that bothers people a lot is that we are making an assumption that we are performing these reactions at a constant temperature. And when you tell someone, oh, it's exothermic, their first thought is, well, temperature is going to go up, so how is that constant? And it has to do with the physical way we do the reaction. We can perform reactions in a water bath so that the water absorbs the extra energy and maintains a constant temperature in the container. There are tricks like that we can use, okay? So we're going to assume we're at a constant temperature so that this will all work. If the temperature changes, delta H and delta S would change, and then you're kind of all out of luck, right? So assume constant temperature. Another way we could do this is by going backwards and doing Hess law type problems. What we can do, for example, is say, look, here's reaction 1. I'm going to flip reaction 2. I'm going to cross out things that show up on both sides. I'm going to add my delta G's. And I'm going to get my final overall reaction, overall delta G for the reaction that I'm interested in. This only works if you know other equations to use and their G values, but it does happen. It is a nice option. A third is like we've done before, where you're just going to do the sum and do products minus reactants. That's only going to work if you have a data table with all your delta G's or a way to calculate them. Now, the weird part, connecting all this to equilibrium, okay? The value of delta G naught can indicate, can tell you, can give you information about the ratios of products to reactants when you're at equilibrium. There is a connection between that. Well, you already learned something that gives you an indication of the ratio of products to reactants. Our K value. K equals products over reactants, right? So that means that there is some connection between delta G and K. That means there is some connection between thermodynamics and equilibrium. That is powerful. That gets us a special equation that we have nicknamed the rat-link equation. Delta G equals negative RT ln of K. ln is natural logarithm. And you should recognize R. Make sure you use the correct R. That's very important. This is how we can make this bridge between our chapters. People tend to forget the rat-link equation. It doesn't get used often. So make sure you make some kind of note to study it. Don't forget it. And when you do get a practice problem using this, make sure you really, really pay attention to it. So we have one little problem. And that is that we are not always at standard state and we're not always at equilibrium. And sometimes we don't know if we're at equilibrium yet or not, right? So it can get a bit confusing because if we're not under the correct conditions, we shouldn't be using delta G naught. We should be using delta G. And at first that sounds weird, but if you think about it, in equilibrium, you also had a similar scenario. You only used K if you were at equilibrium. If you didn't know whether or not you were at equilibrium yet, or you knew for a fact that you weren't, you wouldn't use K. What would you use? You'd use Q. Very similar concept. One of the things that's really frustrating to me as a teacher is that when they redesigned the AP curriculum a few years ago, they took out most of the delta G versus delta G naught pieces of information from the class. And that left kind of a disconnect between the chapters. And so I've actually found it quite difficult for people to understand some of the connections between equilibrium, thermodynamics, when they took out all the math. So I am leaving a tiny bit of it in. I'm leaving enough in that I feel confident you'll be able to answer conceptual questions a little better, okay? I think what they were trying to get away from was teachers only teaching the math. And so their solution was to just tell everyone to take out the math. But that isn't a great solution, okay? So we're going to do a little bit of the math to help us understand the concepts here. When delta G equals 0, you're at equilibrium. We've kind of already talked about that before. That means neither side is more favorable than the other. You can go back and forth, which is what equilibrium describes. However, that does not mean delta G naught will be 0 at equilibrium. Delta G naught will only be 0 if your reactance equals your products at equilibrium. Kind of like K is only 1 if you have equal ratios of everything. And that's really not common, is it? Right? So understanding that delta G being 0 is different than delta G naught is important. So look at this graph for a minute. We have a reaction that's occurring starting on the left. As time goes on, it goes to the right. You have your reactants, you have your products. As you go down this curve, your G is decreasing. That means this is the thermodynamically favorable direction. It is spontaneous going forward. If you look over here, if I were to go up this hill, that would not be thermodynamically favorable, would it? It would not be a release of energy to keep going up this curve, which means at some point it's no longer favorable to keep making products. That's why we don't go to completion most of the time. We don't convert everything to products because at some point it's not favorable thermodynamically to keep going. It's not going to go that way on its own. At this point, if my ratios were over here, the reverse reaction would be favorable. Remember, going backwards would sometimes be better? When you're at the valley down here, your change in G is 0, and that's when equilibrium occurs because neither side is favorable. You get to equilibrium and you're going to stay there unless you're forced to change, right? Unless some outside force comes in, you're not going to change. Well, isn't this very similar to what we looked at when we were learning about K versus Q? We had a graph just like this because they're connected, right? When you're at equilibrium, K equals Q, right? One direction is favorable, the other would not be. Sometimes maybe going backwards is favorable. The things we used to do comparing Q and K apply to our thermodynamics as well. Okay. So, at equilibrium, delta G is 0 and K is Q. If K is larger than Q, you don't have enough products yet. You're going to have to shift right, which means the forward direction is favorable, which would have a negative change in G. If you have too many products, if Q is too big, you're going to have to shift left, which means the forward direction is not favorable. Going forward would have a positive delta G. Now, there is an equation we can use to kind of relate G and delta G naught. It kind of looks like the rat-link equation a little bit, doesn't it? But instead of K, we have Q, and we've added in delta G naught over here. Delta G is when we're at some non-standard, we're not at equilibrium, temperature's all messed up, who knows what's going on, compared to delta G naught, which is when we're at our nice perfect situation. So this is a way that we can kind of make corrections when we're not at our ideal conditions. And we can go backwards from this too. Let's kind of mathematically show ourselves that this can turn into the rat-link equation if we are at equilibrium. So we'll take this adjusted version and we'll remember, hey, at equilibrium, delta G is 0. And at equilibrium, K is the same thing as Q. So let's plug those in. And let's rearrange. Look what we're right back to. We're right back to the negative rat-link. Okay. The reason this connection can be helpful, connecting equilibrium and delta G, is that it will allow us to do some graphing, okay? We're going to be able to graph some things and gain some information from our graphing. So if we have our negative rat-link equation over here, and we know the Gibbs-Helmholtz equation, what can I do with these two equations if they both equal delta G naught? Well, I can set them equal to each other, can't I? And make it look really horrible, okay? This, I think, is one of the most forgotten tricks, most forgotten rearrangements. I would make sure in your notebook you have some reminder to yourself to study this. Don't forget this. It's very helpful. Okay. If you have enthalpy and entropy, you can use that to find equilibrium constant. Very, very, very helpful. So now let's take this rearrangement and keep working on it. I would like to get the natural logarithm of K all by itself. I want this to be set equal to everything else, okay? I end up with this horrible mess, okay? So I divided everything by negative RT. Can you see here? Delta H divided by negative RT. And this part over here was divided by negative RT and ends up looking like this. Then I'm going to do something a little tricky. I'm going to kind of pull out this temperature component. Do you see here? I'm kind of isolating this so that it looks like its own thing. The reason for that is I can now really see that the k value over here, natural log of k, is proportional to 1 over the temperature. And I'm going to kind of start to notice, like, wait a second, that looks like a format my math teacher taught me once upon a time. All this crazy junk kind of looks like y equals mx plus b. And we can graph y equals mx plus b equations very easily. So what I can do is run some experiments, graph my data, and find lots of helpful things. Natural logarithm of k is y. Negative delta h naught over r is m. 1 over t is x. And delta s over r is b. So what I'm going to do is I'm going to graph the equilibrium constant versus 1 over temperature. You remember that k is temperature dependent. New temperature, new k value. So graph a bunch of k values and their temperatures. Natural log of k versus 1 over t. Then using either Excel or a graphing calculator, you can find the line of best fit. And slope is m. M is how you can find delta H. If you can find the slope of your line, you can find your enthalpy. And your y-intercept is how you can find your change in entropy. Okay. So once again, you can see that there are so many rearrangements, so many substitutions. You gotta be good at your algebra. One of the things I've noticed over time, an unintended consequence, is that as we have changed to bell schedules, where we see you fewer and fewer days of the week, as we've been required to make homework shorter and shorter, as we've had fewer and fewer days, all of that, our proficiency and our speed at algebra has decreased a lot because it takes repetition and a lot of practice, okay? Because you gotta develop some muscle memory. So if you're struggling with your algebra, you gotta think of it like a sports practice. You don't go down onto that football field and be the best football player ever without practicing. You don't get perfect at the violin without practicing. When you become very good at something, you will realize how many steps you're taking that you don't have to think about anymore. When someone's playing some super fancy piece of music on their violin, so much of it is muscle memory. And you gotta get your math skills to be at that point, okay? And like I said earlier, right, if you want to start making a little cheat sheet and write down every kind of arrangement so that you can study and practice and all of that, maybe a good idea. Okay. I'm going to do a few odds and ends and reminders, and then the rest will be practice problems, okay? So, when you're using Hess law type problems, you gotta be careful with your k values, okay? When you multiply an equation, you gotta raise k to that exponent. So if you double your reaction, it would be k squared. If you half your reaction, it would be k to the 1/2. When you add your reactions, you multiply their k values. Then and only then can you take your final k value and start doing things like using the Ratlink equation. People will do the Hess law problem for all sorts of things and forget to adjust their K value. So be very careful about that. One thing is that enthalpy is not going to be dependent on pressure, but your entropy is. So the volume of your container ends up playing a role. We usually make assumptions about the experiment's setup so that we don't have to stress about these kinds of things. But, sometimes on conceptual problems, they may ask you how it plays a factor or how it plays a part. So if your entropy is bigger in a larger container, that will affect Gibbs. If your entropy is higher at a lower pressure, that will affect your Gibbs. So enthalpy, not affected. Entropy is affected, therefore Gibbs is affected. All right, now, phase changes are equilibriums. People forget this. You go back and forth and back and forth. During a phase change, delta G is 0. That is a helpful thing because that will allow you to determine what temperature the phase change can occur at. If you know delta G equals 0, you know delta H and you know delta S, you can solve for T. What temperature does that phase change happen at? Now, one of the problems is that we use delta H naught and delta S naught values, but we really shouldn't. But we're going to anyways because we don't really care. Okay? Yeah, they should be adjusted, but it's not even going to be within the margin of error that we care about. Okay? Is it a source of error? Sure. Is it above our pay grade here? Absolutely. Okay? We're not going to worry about it. We're making an assumption to approximate an answer, and that is plenty good enough. It shows us that we understand the concept. Okay. All right. Next, you should have a glue-in that has some practice problems. Okay, I have 4 problems for you. What I would recommend is pause the video, try the practice problems, see if you got the right answer. If not, maybe you should watch that section of the video. I often will give little tips and reminders and hints during the practice problems. It's a good thing to study from and listen to, especially if it's not coming naturally to you. So let's get started. I want us to solve for delta G when you are given delta H and delta S and an equation. Sometimes people will look at the reaction and say to me, where do I put my mole coefficients? Where are those coefficients going to go? Well, if we're using Gibbs-Helmholtz, there isn't a mole consideration, is there? If I was doing products minus reactants and doing the sum of those values, then yeah, I would need my coefficients. But we're not doing it that way. You're going to use Gibbs. If you are not told what temperature you are at, you assume that you're at 25 degrees. We assume that standard is 25 unless told otherwise. All right, how did you do? Let's see what the answer is. So I'm going to use Gibbs. I'm going to plug in my change in enthalpy minus the temperature in kelvins times my change in entropy. And what do you think the common mistake here is? Look at those units. We have kilojoules and we have joules. Does it matter which way you convert? No, not technically, but we usually do delta G in kilojoules. And if you look here, your answers are all in kilojoules, So you got to convert your delta S into kilojoules. So is this a spontaneous reaction? Yep, delta G is negative. Put a big note to be careful about your units, especially if you didn't catch that. It is common for one of the wrong answer choices to have been the answer if you forgot, right? They're going to put that on there to trick you. All right, number 2, calculate the boiling point based on these enthalpies and entropies. What do we know about phase changes? Boiling is a phase change. Well, during phase changes, we know that delta G is 0. I'm going to use Gibbs. I'm going to calculate delta H from my data table minus the unknown temperature times delta S converted into kilojoules. And I'm going to find out that that phase change happens at 284 Kelvin. This is the kind of thing that drives me crazy when they took out the difference between delta G and delta G naught. So how can we do a problem like this if we don't understand that there's a difference? Because without understanding the difference, you don't understand that delta G equals 0 here. All right, number 3. Under standard conditions at 298, what substances will be formed if G is 33.4? I'll give you a hint. You don't have to do a calculation. Just think about what that delta G tells you. Do you notice how it's positive? That means it is not spontaneous in the forward direction. That means it's going backwards. I'm not going to be going this direction. I'm going to be going backwards. I'm going to be forming NH3. All right, let's take the same equation. And this time, I would like you to determine what the equilibrium constant is at 298 based on that G value. So think about an equation you learned that connects delta G naught to equilibrium constant. Well, we can use RatLink. This time, I'm going to convert delta G into joules because my R value is in joules. You could have converted R to kilojoules. That would have been fine as well. Temperature in kelvins and the natural logarithm of K. Solve for natural logarithm of K. And that's not what we're looking for. We are looking for K itself, and you have to remember how to undo a natural logarithm. If you don't remember that, make a big giant note in your notebook. If you want to solve for the thing inside the parentheses, you take E and you raise it to the answer you had up here. Okay. That's a button on your calculator. Not capital E like doing, your times 10 to your exponents. But there's a little button for that magical number that's E. So e to the negative 13.48 gets me this super tiny k value, which makes sense because I should not have a lot of products if it's not a good favorable reaction. Okay. All right. That was so much. I know it was so much. We threw in a lot of math. We threw in rearrangements. We had graphs. We had mental math. We had connections to previous chapters. We had graphing. We had natural logarithms. There was so much, okay? That's why we do it early, because that way we have a long time to practice before that AP test. Trying to learn this the week before the AP test would be a nightmare, wouldn't it? Now we have a year to practice. Okay? All right, everybody, that was it. I hope that was helpful. Bye.